All right, I'm going to go through 3 examples of some analytic geometry questions that get slightly more complicated as we go along. So the first one says there's a triangle with vertices A, B, C, and you have to classify what type of triangle is it. So you have to classify using the sides, so it's either going to have 1, 2, or 3 different sides, or 1, 2, or 3 sides that are the same. So you'll need to use a distance formula, the length of a line segment. And then to classify with the angles, all you really have to worry about is it a right triangle or is it not? So you have to look for any lines that are perpendicular to each other. For space purposes, I'm going to assume that you know and you will write down your length and slope formulas. I feel like I'm going to run out of space, so I'm not going to write them on here. We're going to hope for the best. So one nice way to organize it is to keep similar sides together. So let's start with side AB. I think that's the best I can do. Okay, so side AB. Yeah, distance. So distance of AB, so the length of the line segment AB. And like I said, I'm hoping you know these by now, but here they are. Delta x squared, or x2 minus x1, plus delta y, or y2 minus y1 squared, and then the whole thing square rooted. And then the slope is y2 minus y1 over x2 minus x1, or delta y over delta x. Okay, so the distance of AB, either one can be considered x1 and y1 or x2 and y2. I generally tend to start with any that are negative, put them at the front, then you have less angles to worry about. So the change in x from a to b is -1 minus 2 squared. And then the change in y would be -1 minus 0. Square that and square root. -1 minus 2 is -3. And -1 minus 0 is -1. -3 times -3 is 9. -1 times -1 is 1. So it's approximately the square root of 10. I'm just going to leave it as an exact value like that. I'm not going to simplify this radical or anything like that. I'm not even going to find the decimal. It's going to be good enough for what we need to know. And then I'm going to go to side BC. And I'm going to find the distance of BC. So these ones are all positive values, so it doesn't really matter which one I start with. So 2 minus 1 squared plus 0 minus 3 squared, and then you square root the whole thing. 2 minus 1 is 1, and 0 minus 3 is -3. 1 squared is 1. -3 squared, all squared, is 9. And this will look very familiar. So we have two sides that are the same, which means it's not a scalene triangle, so it's either isosceles or equilateral. And a third color. So side AC is the one we haven't done yet. The distance of AC, delta x will be -1 minus 1 all squared, and then add delta y squared, so -1 minus 3 all squared, and square root that. -1 minus 1 is -2. -1 minus 3 is -4. -2 all squared is 4. -4 all squared is 16. And you'll notice that this is now the square root of 20, which is not the same as the other two, which means that it is an isosceles triangle. Dead spot. Okay. So now we have to decide if it's a right triangle or not. So we're going to look at the slope of each of the lines and see if any of the two intersect at 90 degrees, which means the slopes would be negative reciprocals of each other. So the slope of AB is the change in the y values, -1 minus 0, over the change in the x values, -1 minus 2, which will give us -1 over -3, or 1/3. You'll notice that this is the same as this. Maybe I'll use a different color. This is the same as this. This is the same as this. And we want that to happen. Okay, the slope of side BC, 0 minus 3 over 2 minus 1, which will be -3 over 1, which is just -3. And these happen to be negative reciprocals of each other, which means that it is, in fact, a right triangle. We don't even need to worry about the slope of the other side because we already know that 2 intersected 90 degrees, so we don't care what the slope of the other side is. Therefore, it is an isosceles because 2 sides are the same. Right, because 2 sides are perpendicular. Triangle. Isosceles right triangle. Okay, so that's the first example. The next example says a triangle has vertices P, Q, and R that are given to us. Show that the midsegment joining the midpoints of PQ and PR is parallel to QR and half its length. So this one might be handy to draw a little diagram so we can see what we're talking about here. Doesn't really matter what orientation and stuff. I just tend to draw any old triangle, label the sides P, Q, and R. Sorry, label the vertices P, Q, and R. And then it says that the midsegment joining the midpoints of PQ and PR. So PQ midpoint will be somewhere over here, and PR, the midpoint, will be somewhere over here. And the midsegment joins these two midpoints, so it goes across like this. So I'm going to call these things ST, PQR, ST. You can call them whatever you want, A, B, it doesn't matter. I'm just giving them letters so that when I talk about them later, it'll make a little more sense. So what we're trying to show is that this midsegment, ST, is parallel to side QR, and that the length of ST is half the length of QR. So there's a few things we need to do here. We need to work with the midpoint formula to find S and T. Then we need to find the slope of each one to see if they're parallel or not. And we need to find the length of the midsegment and side QR to show that the length of the midsegment is half the length of QR. So there's quite a few steps here. So we'll start with the midpoint. So I'm going to call it midpoint S. So it's the midpoint of P and Q. And we know the midpoint formula is x1 plus x2 over 2, comma, y1 plus y2 over 2, and its coordinates, so we keep it in brackets. I'm not going to write the formula because I know I'm going to run out of space here. So -2 plus 1 over 2, and then 2 plus 3 over 2. -2 plus 1 is -1 over 2, so -1/2. 2 plus 3 is 5 over 2. So this is the point S. This is the coordinates of point S. Then we're going to find the other midpoint of PR, which I called T. So you could also put midpoint PR and midpoint PQ, but it doesn't really matter as long as everything is labeled appropriately. So midpoint of PR, -2 plus 4 over 2, comma, 2 plus -1 over 2. -2 plus 4 is 2, divided by 2 is 1. 2 plus -1, 2 minus 1 is 1 over 2. So these are the coordinates of point T. Then we need to find whether they're parallel and whether ST is half the length of QR. So we'll find the distance of, let's say, ST first. Distance formula, you find delta y and you square it, and you find delta x and you square it, you add them together and you square root. So delta x would be the change in the two x values. So we'll start with s and we'll subtract t, those x values, and square them, and then add the difference between the y values and square root the whole thing. Negative 1/2 minus another 1 would be negative 3/2 all squared, plus 5/2 minus 1/2 will give me 4/2. 4 divided by 2 is just 2. When you square a fraction, you square the top and you square the bottom. So we get this. We need to find a common denominator and add them together. So 4 will be 16/4. I wonder if I can squish it all in here. Let's see. So this would be 9/4 plus 16/4, because that was 2 squared, which is 4, common denominator. So then we get 9 plus 16 is 25/4. And if you square root a fraction, you square root the top and square root the bottom. So that is the distance of ST. So it is 5/2 units, or 2.5 units long. Now for the next part, we need the distance or the length of PQ. Or sorry, not PQ. QR. Distance of QR. So that'll be 9 plus 16, which is 25. Square root of 25 is 5. So this is, in fact, twice as long as this. 5 divided by 2 is 2.5, and then twice that is 5. So we know that this part is true. Now we need to find the slope of each one. So we'll find the slope of ST. Y2 minus y1 over x2 minus x1. So we got some fractions within fractions here. It's not going to be pretty for a minute, but hopefully it'll work out nicely. So 5/2 minus 1/2, and then negative 1/2 minus 1, which I'm going to write as 2/2 just so I can simplify my fractions easier. 5/2 minus 1/2 will give me 4/2, which is just 2. And negative 1/2 minus another 1 will give me 3/2 negative. Flip the fraction and multiply. So you get negative 4/3 for that slope. And I've officially run out of space, so I'm going to try to squish in the other slope of QR in here. QR. There we go. Same slope, which means they're parallel, and the length, QR, was twice as long as ST. Now, if I had some space at the end, I would make a therefore statement and say, therefore, the mid-segment joining PQ and PR